All right, future educators, it is time for us to establish for realsies one of the most important theorems in all of Euclidean geometry. Let's do it. It's the Pythagorean Theorem. The Pythagorean Theorem says that if I have a right triangle like so, and this little side is A, and this little side is B, and this little side is C, right? Then it's A squared plus B squared equals C squared, right? This is what you read about. You didn't just come to the video without reading. So here's what we're going to do. Any right triangle can be turned so that its hypotenuse, its longest side, is horizontal. That's how the Euclidean plane works. And what we can do is we can drop an altitude from the right angle up here at C down to this point down here, that's D. And what I'm going to have us notice is that this red triangle ADC and this triangle BDC and the original triangle ABC, all of them are similar. All of them are similar. We know this because they all have a right angle and they all have the same acute angles. Red and purple share this, blue and purple share this, so red and blue have to share those angles. So we have three similar triangles. We have this red triangle, ADC. We have a blue triangle. We're going to turn the triangle around so that the right angle is here. This is triangle BDC. And we have the purple triangle. The purple triangle is bigger than the other two, and we're going to turn it around so that the big leg is going up and down, and the little leg is going from side to side. So what do we know about similar figures? We know that similar figures have proportions. So we know that little side here compares to hypotenuse here, as little side here compares to hypotenuse here. Red is similar to purple, so little leg is to hypotenuse as little leg is to hypotenuse. And it is also true that in the blue triangle, big leg is to hypotenuse as big leg is to hypotenuse. And you're thinking, yay. Well, this proportion means that AC times AC equals AD times AB. And this proportion tells us that BC times BC equals DB times AB. Well, let's add. When we add on the left side, we get AC squared plus BC squared. And if that happens to turn out to be AB squared, then we're in great shape. But it doesn't. There's an AB factor, right? But then that other factor is AD plus DB. That's what the distributive property tells us. We can distribute the AB through AD plus DB. But I know what some of you are thinking. Isn't AD plus DB, isn't that just AB? And the answer is yes. And this is the Pythagorean theorem. The Pythagorean theorem says leg squared plus leg squared is hypotenuse squared. And it's true because of similar triangles. There are other reasons that your textbook gives where it might be true for those reasons, and they're all valid. There are many, many, many good proofs of the Pythagorean theorem. I wanted you to see one that wasn't in the textbook so that you could decide if you liked a particular proof better. So if you understood the text and you didn't understand this, you're fine. If you didn't understand the text and you understood this, fine. What you should know is the Pythagorean theorem is well grounded in similarity arguments or area arguments almost every time. So that lets us find the third side of a right triangle. So we imagine that this is 6 and this is 10, and we want to know what that is. And so we know from the Pythagorean theorem that leg squared plus leg squared is hypotenuse squared. And so we can find x just by subtracting and square rooting. Or, if you like, we can find the hypotenuse. I should probably use a different letter because I'm on the same screen. Leg squared plus leg squared is hypotenuse squared. And that is wrong. That is blatantly wrong. That's better. Do you happen to know the square root of 625? I do. It's not very interesting. So this is where math people get the idea that if you have an isosceles right triangle, maybe both of those lengths are 1, you can know what this length is. This length is the hypotenuse. 1 squared plus 1 squared is hypotenuse squared. So the hypotenuse is the square root of 2. So these are the sides of the dreaded 45, 45, 90-degree right triangle. This is also where they get the crazy idea that if you take an equilateral triangle, maybe all the sides are 2, and you drop an altitude, which is also an angle bisector, which is also a median, then you start thinking, well, that's 1. I wonder how big that is. Should probably use a different letter there. Oh, let's use a capital H. And so we can use the Pythagorean theorem on this triangle on the left. 1 squared plus h squared is 2 squared. And that's where people get the crazy idea that h is the square root of 3, if this is 2 and that's 1. And these are the sorts of things that are possible because the Pythagorean theorem is true. In the second screencast for this lesson, we'll take a look at some of the consequences of the Pythagorean theorem, mostly in coordinate geometry. See you there.